A nucleus consists of protons and neutrons. These may be the protons. They have positive charges. The neutrons don't have any electric charges, but protons and neutrons attract each other via the nuclear force, and together they form a nucleus. Typically a nucleus has a diameter of somewhere between 1 femtometer and 20 femtometers. And over that range the nuclear force keeps the protons and the neutrons, the nucleons, together. A single neutron is thus confined in this nucleus, and one can look at this problem quantum mechanically. It is an example of the particle in the box problem, whereby the box may have infinitely high walls. The walls are potential walls. They go from zero potential energy to infinite potential energy. And the question is, what is the energy of the neutron in this box, which might have the dimension of 5 femtometers in the case of a nucleus. So all the other nucleons attract the neutron and keep it inside that box. One can solve the Schrödinger equation to solve this problem and obtains that the energies are discrete. And they are given by Planck's constant squared divided by 8 times the mass of the neutron times the diameter of the box squared times the quantum number n squared. If one calculates energies for this situation using, for the neutron mass, 939.6 MeV per c squared, expressed not in joules but in mega electron volts per speed of light squared, Planck's constant with 6.6 times 10 to the minus 34 joule second, and converts the joule via 1 joule equals elementary charge divided by 1.6 times 10 to the minus 19 times 1 volt. Then one obtains for the first two energies for the neutron. E1 is 8.3 MeV, E2 is 33.1 MeV, and E3 is 74.5 MeV. Those energies correspond to discrete states for the neutron in this infinite box, whereby n1 corresponds to this state, E1. The state with the energy E2 would be a state with quantum number n equals 2 at that point, and the energy state E3 would have a quantum number of 3 and might be drawn there. Now, using quantum mechanics, one can also work out the wave functions for each energy. which are also a function of x. And it turns out that they are sine functions whereby the argument is quantum number times pi times x. In addition, the probability densities can be worked out as psi squared magnitude, and they are proportional to the square of the sine function of the same argument, n pi times x. We can thus draw our potential well once more and include in our diagram not just the energy states but the associated wave functions. N equals 1 is here, 2, 3, and the associated energies are E3, E2, E1. The wave functions are sine functions and look like this. First we have just nodes at the walls. Then for n equals 2 we have a node in the center and the wave function goes through that node, and for n equals 3 we've got 2 nodes, so that the wave function looks like this. The probability densities are the square of the wave function, so they look like this. In all cases they are normalized so that the integral is equal to 1. It is apparent that the probability densities, which indicate the likelihood of finding a particle at a certain position, in this case the neutron, the likelihood of finding the neutron at a certain x, that is the probability density, psi squared. This function has minima and zero intercepts, in fact at these points. And that means that the neutron is never found at those points. It's much more often found at local maxima of the probability density, but not exclusively. It can also be found in between, but not at the node.